Mhm. Thanks everyone for being here. Sorry, Alan's just running his intro. So if you are just now tuning in to Ether Cosmology, bear with me for just a second here.
Time to break out the quadratics, boys.
And get ready to break out the quadratics.
All right, Toby, we are live if you want to bring us in, sir.
Excellent. Hello, everybody, over at Ether Cosmology and over at Space Audits and over at ADL, the good one. Tonight we are going to be doing some reading. We're going to be doing some reading of more of Shankar's physics. So we're going to dive right back in where we left off and just kind of go from there, and then see if anything else comes up that that anyone wants to read, or kind of just see, probably just kind of do it like we did last week, where we'll just read this until we get bored, and then yeah. So I believe we were somewhere in section 2, I thought. But for some reason I was...
Page 44.
Oh, thank you, sir.
Yep.
Perfect. All right, so I'll go ahead and start us off here in section 2.5. Let's take a particle in the x negative y plane that moves from r at a time to r plus delta r at a time t plus delta t, as in figure 2.5. At time t, its location is r equals ixt plus jyt. At t plus delta t, it is r plus delta r equals I times x times t plus delta x plus jyt plus delta y. And if you're just listening, then you're missing some order of operations in that. Do that so that delta r equals I delta x plus j delta y. And by the usual limiting process, v equals the limit of delta t approaching 0. So you have delta r over delta t equals the derivative of r with respect to t equals I, the derivative of x with respect to t, plus j, the derivative of y with respect to t. And then you get this nice little visualization here. J delta y, I delta x.
Just another axial component breakdown.
Gotcha. Let's read what they say here underneath the figure. It says, the particle moving along some curved path goes from r at time t to r plus delta r at time t plus delta t. So r delta r, t delta t. The velocity v is the limit of the ratio delta r over delta t as delta t approaches 0, and thus parallel to delta r, which eventually becomes tangent to the curve. Okay. When you move just along the x-axis, you wait a small time delta t, and you move by an amount delta x, and their ratio gives the velocity in the appropriate limit. When you move in the plane, your position and its change are both vectors. Can you see why the derivative of a vector is also a vector? Because delta r, the difference in the vector between two times, is itself a vector. Dividing it by delta t is like multiplying by 1 divided by delta t. But we know that when we multiply a vector by a number, we simply rescale the vector. So the limit will become some arrow, and we call the instantaneous vector So the limit will be some arrow that we will call the instantaneous velocity vector. It will be tangential to the curve RT and point toward the instantaneous direction of travel. If I gave you the location of a particle as a function of time, you can find its velocity by taking derivatives. For example, if I say a particle's location is r equals t squared, I plus 9t cubed j, then its velocity at time t is v equals 2ti plus 27 times t to the second power j. Sorry, so I'm just like, so you can find its velocity by taking derivatives. So, okay, so there's the derivative. You can take a derivative of the velocity of the second order derivative position to get the acceleration vector. At equals dv over dt equals, so the d, what is going on here with the d squared?
Isn't that the actual indication of the second derivative, squaring the d?
Ah, okay. So the derivative of the velocity or the second derivative of the position to get the acceleration vector. Okay. So we're taking the derivative of the velocity, which is with respect to time. We're taking the second derivative of the position to get the acceleration vector. That's going to equal 2i plus 54tj. You can then also multiply a by the mass m, which is the scalar unaffected by rotations, to get vector ma, which Newton's law equates to another vector, the force F. Even though we started with one example of a vector r, we're now finding out that its derivative has to be a vector, and the derivative of the derivative is also a vector. When you learn relativity, you'll find out there's again one vector that's staring at you, the analog of the position vector, but with 4 components. But more vectors can be manufactured by multiplying vectors by scalars, like mass, or taking derivatives with respect to a parameter that plays the role analogous to time. Oof. Okay, it'll be fun to get into that. Here is an illustration of vector addition and differentiation. Imagine an airplane in flight, as depicted in figure 2.6. Let RPG be the location of a fixed point in the airplane, say the tail with respect to a fixed point on the ground. Imagine that in the airplane there is a ball located at RBP and measured from its fixed point, or from this fixed point in the airplane. By vector addition, the location of the ball with respect to the ground is RBG, which is going to equal RBP plus RPG. So there you go. Position of the ball relative to some origin on the ground, RBG, is the vector sum of the position of the ball relative to the tail of the plane, RBP, and the position of the tail of the plane, RPG, relative to the ground. Upon taking a time derivative, and in the same notation, the law of composition of velocities follows. VBG equals VBP plus VPG, which says the velocity of the ball as seen by a person on the ground is the velocity of the ball relative to the airplane plus the velocity of the airplane relative to the ground. Taking yet another derivative, we may relate the accelerations of the ABG equals ABP, which equals plus APG. In the special case of an airplane moving at constant velocity APG equals 0, then we find ABG equals APG. Which means, in this case, the acceleration of the ball is the same as the measured by an observer on the ground and an observer on the airplane. These results will be recalled in our study of relativity. So, but they said when that was 0.
Yeah, because it's constant velocity, there's zero acceleration.
Yeah, that's just, yeah, got it. Now we'll take a concrete problem where you will see how to take derivatives to obtain very useful results. I'm going to write a particular case of RT. RT equals R times I times the cosine of omega t plus j sine omega t, where R and omega are constants. What is going on as a function of time? What's this particle doing? Look at the length squared of this vector. Rx squared plus Ry squared equals r squared times the cosine squared of omega t plus sine squared of omega t equals r squared. That means the particle is going around in a circle of a radius r, as shown in figure 2.7. The x component is r cosine omega t, and the y component is r sine of omega t, where omega is a fixed number. As t increases, this angle omega t increases, and the particle goes round and round. Let's get a feeling for omega. As time increases, the angle increases, and we can ask how long it will take the particle to come back to the starting point. Suppose the starting point was on the x-axis. As t increases, omega t increases, and the particle will come back at a time t such that omega t equals 2 pi. Here's omega t going around with the radius r at an angular velocity omega. So they're just kind of showing the way. This is a great description of angular velocity and what that specifically means.
I think I would describe the rate as omega t, that it's omega per t almost, because they seem to be slicing t into multiples of it in order for it to return to the full 360 point. Does that make sense? Or am I just out of there?
Omega of t, is that what you're saying?
Yeah.
Yeah.
Not to worry.
Yeah, no, that makes
T
sense.
just moves. I don't think there's anything special about T. I mean, it's just the time,
The time it took to get to omega was the t.
yeah, the time for it to keep doing circles and then it'll become cyclical. Well, yeah. So yeah, whatever. I mean, you would plug in the T or solve for the T, but I mean, it's just the time, though. I think, right?
Well, it's the time it went from y equals 0 rotating up those what looks to be 45
It's
degrees
kind of
in the diagram.
it's kind of cool, actually, the way it seems like they have the little tangents coming off. I mean, so it's a cool way to see the vector thing with the J and the I.
Here we go. They're saying here, thus omega is related to the time period t by omega equals 2 pi over t equaling 2 pi function. I guess a function of 2 pi?
It's just the reciprocal, the frequency.
Where... So that's the reciprocal
Flip the
specifically?
time and you get frequency.
Okay. Is the frequency... So this is the reciprocal of 1 over t?
You got it.
Great,
Yeah.
thank you. Where the reciprocal of 1 over t is the frequency or number of cycles per second. It is measured in hertz, which stands for hertz. Since in every cycle the particle rotates by 2 pi and it completes f revolutions per second. Omega equals 2 pi f is called the angular velocity and measures the radians swept out per second. Notice that in equating a full cycle to 2 pi, I am using radians and not degrees to measure angles. For those who have not seen a radian, it's just another way to measure angles. We're in a full circle, which we used to think was worth 360 degrees, now equals 2 pi radians. Since 2 pi is approximately equal to 6.3, a radian is roughly 60 degrees. You will see the advantages of using radians later. For now, just remember that a half circle, instead of being 180 degrees, will now be pi radians, and a quarter circle will be pi over 2, and so forth. How fast is this particle moving? It's going around a circle. The angle is increasing at a steady rate omega, and so we know it's going at a steady speed. Let us verify that by computing the velocity. Vt equals the derivative of rt with respect to t, and that equals r times I times the d times the cosine of omega with respect to t, or so it's the derivative of the cosine of omega with respect to t with respect to time plus j times the d times the cos or the sine of omega with respect to t, or omega of t with respect to t, and that equals r omega times negative I sine of omega t plus j cosine of omega t. At t equals 0, the velocity is v equals r omega cosine of 0, j equals r omega j. So it is moving straight up at speed v equals omega r. You may verify that it has the velocity as shown in the figure at later times. The magnitude of the velocity is always omega r, although the direction is changing. From the figure, we see it remains tangential to the circle. The constancy of the speed v at an arbitrary time may also be established by computing v squared equals omega r squared times sine squared of times omega t plus cosine squared, sine squared of omega t plus the cosine squared of omega t equals omega r squared. And v equals omega r. Okay. Remember, the tangential velocity is v equals omega r. Let's take the derivative of the derivative to find the acceleration a and its magnitude. A equals negative omega squared times r times I times the cosine of omega t plus j times the sine of omega t equals negative omega squared r, and then a equals omega squared r. That's a very important result. It tells you that when a particle moves in a circle radius or a circle of radius r at a constant speed v, it has an acceleration called the centripetal acceleration, directed towards the center and of magnitude a equals omega t, r equals omega r squared over r, which equals v squared over r. This acceleration at constant speed reflects the fact that velocity is a vector, and you can change the velocity vector by changing its direction. For example, if a car is going on a racetrack and the speedometer says 60 miles per hour, the layperson's view is that the car is not accelerating. But you will say from now on that it indeed has an acceleration equal to v squared over r, even though no one's stepping on the accelerator or the brake. Suppose the particle is not moving fully around a circle, but traversing just a quarter of the circle. When it is traversing the quarter of a circle, it has the same acceleration directed toward the center of the quarter circle. In other words, you don't have to be moving actually in a circle to have the acceleration v squared over r. At any instant, the curve you are following can be locally approximated as part of the same circle, and in the formula a equals v squared over r, the acceleration is directed towards the center of that circle. R is its radius, and v the instantaneous tangential velocity. All right. Section 2.7, Projectile Motion. I want to consider a particle for which r0 and v0 are the position and velocity at t equals 0, and which has a constant vector acceleration a. What is its location at all future times? By analogy with what I did in one dimension, rt equals r0 plus v0t plus 1/2 of at squared, once you know r0 and v0, you can find the position of the object at all future times. Let's take one simple example. Somebody in a car has decided to drive off a cliff as shown in figure 2.8. Okay. We want to know when and where the car hits the ground. We pick our origin 0, 0 at the foot of the cliff. Let the height of the cliff be h. The car is traveling with some initial speed v0x in the horizontal direction. Equation 2.59 is really a pair of equations, one along x and one along y, with a equals negative jg, v0 equals v0xi, and r0 equals hj. Separating out the components, xt equals 0 plus v0xt plus 0, yt, or y of t, or t of y, equals h plus 0 minus, or h plus 0 minus half gt plus, or squared. Notice that the evolution of the two coordinates is completely independent. When time t asterisk, the time t star when the car hits the ground, y equals 0, satisfies the equation. The car flies off a cliff at 0h and lands at d0. A projectile is launched with initial velocity v0 equals I plus the square root of 3 times j meters per second. The range is r equals 0.35 meters, and the maximum height reached is y max equaling 0.15 meters. So 0 equals h time, or h minus 1 half gt star, or to the power of star 2. And t star equals the square root of 2h over g. This is exactly how long it would take to hit the ground had it simply toppled over the edge from rest. The horizontal velocity does not delay the crash one bit unless you take into account the curvature of the Earth. As to where the car lands, the location is given by parenthesis x parenthesis t to the power of star. So we have t star of x comma 0, and then that's going to be equaling to d0, where d equals d0x t star, and that's going to equal v0x times the square root of 2h over g. Finally, the problem of projectile motion is depicted in figure 2.8. B. You will find the projectile from 0, 0 with some velocity v0 at some at some angle theta. It will go up and then come down, moving horizontally at the same time. Where is it going to land? What is the maximum height, y max, to which it rises? One moment, I'm going to take a quick drink of water. What is the maximum height, y max, to which it rises? With what speed will it hit the ground? At what angle should you fire your projectile so it will go the furthest? Here are the equations that contain all the answers, namely equation 2.59, written out in the component form. So x of t equals, or t of x equals 0 plus v0x t, or v0x times t equals v0 times the cosine of theta times t. And then y of t equals 0 plus v0yt minus half of gt squared, which is going to equal v0 times the sine of theta times t minus 1/2 of gt squared. You can solve them, but it is good to have an idea of what's coming. Imagine you have this monster cannon to fire things. It has a fixed muzzle speed, v0, but allows you to fire at any angle. How do you aim it so the ball goes as far as possible? There are two schools of thought. One says aim at your enemy and fire horizontally. Then the ball lands on your foot because it has 0 time of flight, assuming the cannon is at 0 height. Okay. The other school says maximize the time of flight and point the cannon vertically. It goes up, stays in the air for a long time, and lands on your head. Then it hits you. The correct answer is somewhere in between 0 and 90 degrees, equaling pi over 2. The naive guess, 45 degrees equaling pi over 4, turns out to be correct. Now I want to show you how to use the equations to prove this. What's the strategy for finding the range? You see how
Oh, but he
long...
forgot about the curvature of the Earth there.
Mm.
Continue.
You see how long the ball is in the air and multiply that by the constant horizontal velocity v0 cosine theta. Again, let t star be or t to the power star be the time when it hits the ground. The y equation 0 equals t star times v0 times sine theta minus half of gt star has two solutions. Hold on now. The star is just a variable here, right?
Yeah, it's kind
I
of like
think the
T
T star
final.
is yeah, exactly. It's the moment when it hits the ground. So you want that to be as far as possible in the
Okay,
way that they're solving this for the angle.
thank you. So that at t star it has a value v t star, and so that t star has a value v times t star equals v0 sine theta minus g times 2v0 times sine of theta over g, equaling negative v0 times the sine of theta, which is just the opposite of the initial vertical speed. The magnitude of the final velocity is the same as the initial one, since reversing one of the components of v does not change its length. There are endless variations. You pick some point off the ground at xy and want the projectile to arrive there. You are given the launch angle theta and have to find the launch speed v0. How do you do that problem? You assume the projectile arrives at the destination xy at some time t star. You go to the x equation and demand that x of t star equals x and solve for t star. Plug this time into y and demand that y times t star, or t star y equals y, and solve for v0. Sometimes the problems are embellished to make everyone feel involved. For example, instead of a ball dropping, nowadays there's a monkey or a horse that is falling down. So people in life sciences can say, hey, we should learn physics, since it seems to have applications to our subject. All those gyrating creatures are very interesting and look great in color, but in the end, you are told, treat the horse as a point particle. If you're going to treat the horse as a point particle, why include its color picture? But I agree, there are times when only a horse will do. When the Godfather wants to get the contract for Johnny Fontaine, he doesn't tell his consigliere. Stone, I know I butchered that.
Consigliere.
Conciliere.
Thank you.
Consigliere.
Consigliere. Hey Tom, put half a point particle on Jack's bed. That would have been a disastrous approximation. By the way, don't forget to treat the falling car in figure 2.8 as a point particle. All right, who wants to popcorn?
Dude, I know my boy. I know my boy Scott's ready to popcorn.
Yeah, I'll have popcorn.
All right,
Awesome, bro.
popcorn
Thank
Scott.
All right, so reading away, I guess. Is that okay?
Yes, sir. And then
3.1.
any additional inputs you want to throw in and break down, that'd be super helpful too. So
Okay,
if you think
cool. It's hard though. Actually, I don't know how you guys feel, but trying to keep up with it all, you know, takes some effort.
This is your chance to crack the whip.
All right, well, we'll see how it goes. Introduction to Newton's laws of motion. This is a big day in your life. You're going to learn Newton's laws in terms of which you can understand and explain a very large number of phenomena, especially the globe Earth. It's sorry, little humor insertion.
We like
No,
that part.
you're great.
Okay, cool. It's really amazing that so much information can be condensed into 3 laws. Your reaction may be that you've already seen Newton's laws, that you've applied them in school. I realized fairly late in life that they are more subtle than I first imagined. It's one thing to plug in all the numbers and say, I know Newton's laws and I know how they work. But as you get older and you have more spare time, you think about what you're doing. Wish a lot of people that had learned these would would do that. Think about what they were doing or how they apply. This is something I've had the luxury of doing, and I realize the laws are more tricky. I want to share some of that understanding. The first law, or the law of inertia, says if a body has no forces acting on it, it will maintain its velocity. In other words, in the absence of external forces, a body at rest will remain at rest, and a body in motion will retain its velocity. It is not surprising that a body at rest will remain so if not acted upon by a force. We see that all the time. I place an eraser on the table. It will stay put unless I do something to it. The great discovery that Galileo and Newton made was that you don't need a force for a body to move at constant velocity. You don't see that in daily life. Everything seems to come to rest unless you keep pushing or pulling it. We all know that the reason things come to a halt is that there is always some friction or drag bringing them to rest. If you take a hockey puck on an air cushion and give it a push, it seems it can travel for a very long time. Galileo and Newton abstracted from this an ideal situation in which friction was totally eliminated, and the bodies kept moving forever with no help. If you go to outer space, you can check for yourself that if you throw something, it will go on forever without your intervention.
Put that on my
It's
task
in the
list.
yeah. It's in the. I need to scroll. If you it's in the nature of things to retain a constant velocity. It is not velocity, but a change in velocity that calls for a force. The law of inertia is not valid for everybody. I'll give an example from your own life. You go on an airplane, and then, after the usual delays, the plane begins to accelerate down the runway. At that time, if you leave anything on the floor, you know it's no longer yours. It's going to slide backward, and the physicist in the last row is going to collect everything. Always good with the physicist humor. Um, that is an example of a frame in which the law of inertia does not work. Bodies accelerate with no applied force. Once the plane stops accelerating, the law of inertia becomes operative. It falls when it decelerates during landing, when everything now slides to the front. Newton's law of inertia works for you. You are called an inertial observer, and your frame of reference is called an inertial frame. The plane that's taking off is not an inertial frame, but the one that is cruising is. The Earth seems to be a pretty good inertial frame because if you leave something at some place, it just stays there, unless the thing is your cell phone and the place is Grand Central Station. But this is not a violation of Newton's laws, just the laws of New York City. Although not every frame is inertial, there are plenty of inertial frames to go around. If you find even one inertial observer, namely one person for whom this law of inertia works, I can find for you an infinite number of other people for whom this is true. Who are these people? They are people moving at constant velocity with respect to the first initial observer. Suppose you're in a train and you're moving past me with velocity u, and the bold face is also indicating the direction or vector, just like the I or J thing, that it has a direction. Velocity u, and we both look at some object with no forces on it. We will not agree on its velocity or the velocity of anything. Things at rest for me will be moving backward for you at velocity negative u, and everything at rest in your train will be moving at velocity u according to me. In short, you and I will differ on the velocity of any object by our relative velocity. We will agree on the acceleration of any object since it is unaffected by adding a constant to velocity. Adding a constant velocity to objects does not change the fact that those which were maintaining constant velocity still maintain a constant but different velocity. Thus, neither is every observer inertial, nor is an inertial observer unique. You must know the Earth is not precisely inertial. The Earth has an acceleration. Can you see why?
Oh, does it now?
Yes. Can you see why, Stone? Yes, it's spinning around itself and going around the sun, both of which constitute accelerated motion. Case closed. I'll see you guys later. Sorry.
Yeah, punch out.
All right. But the acceleration due to motion around the sun at speed v and radius r is a equals v squared r equals 0.006 meters per second squared, which is a very small number, say, compared to g. The same goes for the acceleration due to the Earth's rotation about its own axis, which is roughly 0.03 meters per second squared, or roughly g over 300 at the equator. So the Earth is supposed to be accelerating when it
Yeah.
spins?
That's the rotational function right there. That's 3 centimeters per squared second of acceleration relative to ECE, right? Just out of
Well,
the
I feel
middle
like
of
I'm
it
missing
because it's
something
spinning.
then. Well, oh, it's like the centripetal acceleration. See, I'm thinking if it's accelerating, then
Centrifugal, yeah.
eventually it's just yeah. Or is would it be centripetal or there's centrifugal?
It's the
Centrifugal.
G one.
All right.
It's the spinning away centrifugal one.
Okay. All right. The first law might seem tautological
Yes.
because we never see anything that retains its velocity forever. And every time we see velocity change, we say that a force is acting. But it's not a big hoax. No, it's not. Because you can set up experiments in free space far from everything where objects will, in fact, maintain their velocity forever. It's a useful concept even on the Earth because the Earth is approximately inertial.
Oh, I hate dangerous, unquantified statements like that.
Hilarious.
Can we continue?
Approximately inertial.
Yeah, go for it, man.
It's fun to read, ironically.
Yeah, that leaves a lot of wiggle room right there. Uh, Newton's second law, 3.2, Newton's second law. Newton's second law says if a body has an acceleration a, and again, vector, then you need a force, vector F equals ma, to produce that acceleration. In this chapter, we will focus on one dimension and write F equals ma, where F and a are along the x-axis. A few words about units. Acceleration is measured in meters per second squared. Mass is measured in kilograms or kg. So force has units, kilogram meters per second squared. We get tired of saying that long expression, so we call that a Newton, denoted by N. If you had invented mechanics, we'd be calling it by your name, but it's too late for you now. Might be cursing that name or something, but here's a typical problem that you have solved in your first pass at Newton's laws. A force of 36 newtons is acting on a mass 4 kilograms. What's the acceleration? You divide 36 newtons by 4 kilograms and you find it is A equals 9 meters per second squared. Also, I'll just throw this in. It's super basic, but I mean, yeah, to get those units, you have to remember the Newton is the whole kilogram meters per second squared. So that it becomes 9 meters per second squared. Just in case anyone any questions there. You say, okay, I know Newton's laws. It's actually more complicated than that. Take yourself back to the 17th century when Newton was inventing these laws. You have an intuitive definition of force. When somebody pushes or pulls an object, we say a force is acting on it. Suddenly, you were told there is a law, F equals ma. Are you better off in any way? Can you do anything with this law? What does it help you predict? Can you even tell if it's true? Something.
Yo, my bad. I accidentally
Whoops.
goofballed my my navigation here.
That's cool.
Linux did
we're,
right up, I think.
Yeah, we're getting GPS to rein us back
There
in.
you
1
go.
second. Okay, we're back.
One more page.
Yeah. Oh, good GPS. Oh, wait. I think you were there
Here's a
actually
body that's
before.
moving. That you're in it now. Can you tell if it's true? Third line.
Oh yeah. Better off in any way. Can you do anything with this law? What does it help you predict? Can you tell if it's true? Here's a body that's moving. Thank you. Is Newton right? How are we going to check? Well, you want to measure the left-hand side and you want to measure the right-hand side. If they're equal, you will say the law is working. What can you measure in this equation? Let's start with acceleration. What's your plan for measuring acceleration? What instruments will you need? If you say a watch and ruler, that would be correct, provided by ruler, you don't mean Queen Elizabeth. Here is your ruler, and here's a Rolex. Tell me exactly how you plan to measure acceleration. Everyone seems to know the answer. First, let it go a little distance and take the distance over time. But that gives you the velocity now. Let it go a little more and repeat the velocity measurement. Take the difference of the two velocities and divide by the difference of the two times, and you have got the acceleration. Since the body is moved a finite distance in a finite time, this gives the average acceleration. You want to make these 3 positional measurements more and more rapidly. In the end, as all the time intervals shrink to 0, you will measure what you can say is the acceleration now. The second derivative equals a of t, defined in calculus. Back to testing. If what Newton told you is right, you see an object in motion, you measure A, and you get a certain numerical value, say 10 meters per second squared. But that's not yet testing the equation because you still have to find F and M. What's the mass of this object? One common idea is to take a standard mass and balance the unknown mass on a seesaw by adjusting its position. It's typical. But suppose you were in outer space. There's no gravity. Then the seesaw will balance even if you put a potato on one side and an elephant on the other side. What you are doing now is appealing to the notion of mass as something that's related to the pull of the earth on the object. You've got to go back and wipe out everything you know. If F equals ma is all you have, there is no mention of the earth in these equations. You only know how to measure A, but not the other two. So you have a problem. You cannot say that since F equals ma, it follows that M equals F over A. That is circular reasoning since you have not told me how to measure F either. Let me give you a hint. How do we decide how long a meter is? You seem to know that it is arbitrary. A meter is not deduced from anything Napoleon or somebody said. The size of my ego is 1 meter. That's a new unit of length. Seriously, at the National Bureau of Standards, there used to be a rod made of some special alloy in a glass case, and that defined the meter. There are fancier definitions now, which I know you guys know well because I've
Actually,
definitely
I
heard.
saw an original definition of the meter based on the definition of a centimeter, and that's one drop of water landing on something perfectly flat with no surface tension, that it spreads out to a meter in or a centimeter in diameter, and they seem to have extrapolated from there.
Wow,
That's fascinating.
that's an interesting one.
It's trippy, isn't it?
Huh?
Yeah.
Yeah.
It shouldn't be based on the speed of light or anything, you know?
Yeah, keep that out of it. In that case. But so let us stick to the simple one. Then I ask, see the thing on units for more details on definite units. Then I ask you what is 2 meters and what is 3 meters. We have ways of handling that. You take the meter and attach it to a duplicate, and that's 2 meters. You can cut it in half using dividers and compasses. You can split the meter into any fractions you like. Likewise for mass. We will take a chunk of some material and we will call it a kilogram. It's a matter of convention, just like 1 second is some convention. I'm going to give you a glass case that contains a block of some metal defined as 1 kilogram. Then I give you another object, an elephant. What's the mass of the elephant? There's a hint. I also give you a spring. We cannot do the seesaw experiment because it requires gravity. A spring, on the other hand, will exert a force even in outer space. Here's what we do. We hook one end of the spring to a wall and we pull the other end. Wait, I thought we were in space. But okay, we hook one end of the spring to a wall and we pull the other end from its equilibrium position by some amount and we attach the 1 kilogram mass to it. We don't know what force it exerts, but it will not matter. We let it go and measure the initial acceleration A1. Then we bring the elephant, another point particle, of unknown mass ME, pull the spring by the same amount so it can exert the same force and find the acceleration AE of the elephant. Assuming only that the same extension produces the same force in 2 cases, we have 1 times A1 equals mass of the elephant times the acceleration of the elephant. Mass of the elephant equals 1 times A1 over AE. Oh, so the 1 is just that particle or whatever. Once you have the mass of the elephant, you can use it to measure any other mass, MO, by using MO equals mass of the elephant times the acceleration of the elephant over the acceleration of whatever else you're looking at there.
The
Where
potato.
AE and AO are produced by, the potato thing, produced by the same force. There are subtleties even here. For example, how do we know that when we pull the spring the second time with the elephant, it will exert the same force as the first time when the 1 kilogram was attached to it? After all, springs wear out. That's why you change the shock absorbers in your car. First, we have to make sure the spring exerts a fixed force every time for a given extension. How are we going to check that? We don't have the definition of force yet, but we can do the following. We pull the 1 kilogram mass and let it go, and we note the acceleration. Then we pull it again by the same amount and let it go. We do it 10 times. If every time we get the same acceleration, we are convinced this is a reliable spring that is producing the same force under the same conditions. On the 11th time, we pull the spring and attach the elephant. With some degrees of confidence, we can say we are applying the same force on the elephant as on the 1 kilogram mass. Why is this discussion so important? Because you need to know that everything you or I write down in the notebook or on the blackboard as a symbol is actually a measurable quantity, or as they say in France, des miserables. You should know at all times how you measure anything that enters your theory or calculation. If not, you are just doing math or playing with symbols. You are not doing physics. This discussion also tells you that the mass of an object has nothing to do with gravitation, but with how much it hates to accelerate in response to a force. Newton tells you forces cause acceleration, but the acceleration is not the same on different objects for a given force. Certain objects resist it more than others. They are said to have a bigger mass. We can be precise about how much bigger by saying if the acceleration of a body in response to a given force is 1/10 that of 1 kilogram mass, then the mass of the body is 10 kilograms. For some reason, I'm thinking
That's
about
just algebra.
density as yeah. It's just also the thing with the mass. You know, I mean, small things can have more mass if they're more dense. It seems like they kind of anyway. 3.3, 2 halves of the second law. We've seen how all objects can be attributed to mass. Now go back to the spring. I want to know how much force, f of x, it exerts when I pull it by a certain amount x, which is measured from the point when the spring is neither compressed nor expanded, as shown in figure 3.1. Don't know if we want to check that out. Attached to the spring. Oh yeah, just pulling it out. And then yeah, this Hooke's law thing is a favorite of like beginning calculus, which I'm sure we're gonna get treated to. We've seen how long. Now go back to the spring. I want to know how much force. And if x is positive, it means the spring is stretched. If it's negative, it means the spring is compressed. Now I can measure f of x for any given x because I can measure the acceleration it produces on a known mass m and use f equals ma. So I pull it by various amounts, measure f, and draw a graph. It will be a straight line with some slope, negative k, for small values of x. Where k is called the force constant. I think of the spring is where they're headed. The minus sign says if you pull it to the right so that x is positive, the spring will exert a force in the negative direction. If you compress it, then x is negative and the spring will exert a force in the direction of increasing x. All springs will have a graph like this for small enough distortions from equilibrium. Beyond that, the line may bend or the spring may even snap. In any case, we now have a way to measure k for any given spring in the regime when f of x is linear in x. I want you to think about the two equations f equals ma and f equals negative kx. If the first one is Newton's law, then what's the other one? What's the difference between saying f equals negative kx and f equals ma? Let me paraphrase the answer I usually hear from students. F equals ma is universally true, independent of the nature of the force acting on a body, while f equals negative kx is only describing the spring. Essentially correct, and I will now elaborate. The cycle of Newtonian dynamics has two parts. First one is to find the acceleration A of a body, the force on which is somehow known, using A equals F over M. Force F is the cause, and the acceleration A is the effect, and A equals F over M is the precise relation between them. The second is to deduce experimentally what force F will be acting on a given body at any given time. For example, if a mass is attached to a spring that has been extended by x distance, we must do the experiment to find that the spring force is F equals negative kx. Newton does not tell us that. He never tells us what F is in a given context, with the exception of gravity, where he also furnished the left-hand side of F equals ma with his law of universal gravitation. If two sort of I'm big on this Coulomb's law of replacement thing, and it's just funny that it has it right here. Replacing the gravitation.
Interchangeability, quite.
Yeah, it's like who would have thunk?
Wait a minute.
If two light charges repel each other.
You're telling me the kinematic and dynamic equivalence has been hiding right here the whole time in the instruction book?
So it would appear.
Wow. Jesus, dude. GG. All right.
If two like charges repel each other, so if two like charges repel each other, we need Coulomb's law to tell us that the force varies as 1 over r squared. The nuclear force, say between a proton and neutron. Just since I'm talking here, I want to throw this in about the proton and neutron as a subject for perhaps a future talk, but I'd like to hear more about radioactivity, and kind of the atom in the context of the ether, this new science. Sorry, I think I think you need to go up just slightly, or no?
Yeah, back 2, 3
Sorry.
lines. I also wanted to point how he very auspiciously just tossed out universal gravitation there and somehow not able to relate it to 1 over r squared when we all know Newton's equation is over r squared. All of a sudden, it just doesn't apply to universal gravitation because they're assuming that all of our experiments are taking place at sea level where r does not change. See that? Little snag in there. Little logical snag about the dynamics of the situation that he just tosses out for sake of simplicity, and I bet they never come back to it.
Yeah. Yeah. Interesting. Okay, so if two like charges repel each other, we need Coulomb's law to tell us that the force varies as 1 over r squared. The nuclear force, say between a proton and neutron, falls exponentially with distance. Surely Newton did not tell us this, but once we have experimentally determined a new force F, we can use his second law to deduce the A it would produce, assuming classical mechanics is applicable. When a new force like the electric force is discovered, the F due to it can be measured in one of two ways. One is to compare it to a known force that balances it. For example, to find how the repulsive force between two charged bodies varies with distance, we can glue them to the two ends of a spring of known K and measure by how much it is extended in equilibrium. Another way is to release the charges of known mass from rest with some separation. Measure the initial acceleration of either, and then compute MA. Physicists are busy either finding A from F, as when computing the orbit of a satellite given the force law for gravity, or F from A, as when stretching springs to find K, or dropping apples from trees to measure the force of gravity. Now, a small digression on gravity. Consider a body near the surface of the Earth, the force of gravity on it being F equals negative mg, where g equals 9.8 meters per second squared. I have to say, for me, being somewhat new to this, it's kind of it's painful, just having to spend so much time pretending like the whole gravity thing is what it's cracked up to be.
Quite.
Thanks. Yeah. So F equals negative mg, where g equals 9.8 meters per second squared. That's something you find out by dropping things from a tower. Consider A in the field of gravity. We find it is A equals negative mg over m equals negative g for all bodies. That's a very remarkable property of the gravitational force, the cancellation of m. If you look at the electrical force on the proton and electron, for example, it's not proportional to the mass of either object. It's proportional to the electric charge of the object. Therefore, when you divide by the mass to get the acceleration, the response of different bodies is inversely proportional to the mass. Gravity has a remarkable property that the pull of the Earth is itself proportional to the mass of the object. So when you divide by the same m to find A, it cancels and everything falls at the same rate on the surface of the Earth. In fact, that is a property of gravitational fields anywhere, even in outer space. Everything, gold, silver, diamonds, particles, elephants, all accelerate the same way. This remarkable fact was known for a long time, but it literally took an Einstein to figure out why nature behaves in that fashion. Yeah, all this propaganda seated in there. I mean, like Einstein, the genius, BS.
We
Why the
would
two
just
masses
be.
associated with a body are equal.
No, you're good. Go ahead.
Okay. Why the two masses associated with body are equal. One is the inertial mass, which is how much a body hates velocity change, how hard it resists acceleration, the mass in F equals ma. That quality can be measured far from planets, far from everything. The other is gravitational mass, which is the measure of how much it is attracted to the Earth or any other body. There's no reason why these two attributes had to be equal. Is this just an accident, or is it part of a big picture, cartoonish picture? It turns out that it's part of a big cartoonish picture called the general theory of relativity. Boo. Here is Albert
Cartoonish
Einstein's
indeed.
description of. Yeah, sorry. I hope it's okay. Just a little editorializing there, but
No,
Not
no,
at
please
all,
keep it
yeah.
coming.
With
Please
the
keep it coming.
crowd.
We've gotten feedback that people like when we interject a little bit. So
Color
Okay, cool.
commentary.
whatever you're comfortable with, go for it.
All right. Turns out that it's part of a big picture called the general theory of relativity. Here is Albert Einstein's description of gravity. Yeah. Imagine a stream and some kids dropping various leaves or paper boats in it. No matter what they drop, within reason, the object's trajectory will follow the flow lines of the water. The path of all objects is predetermined. This is what gravity does to space-time. It defines trajectories for objects. Anything you release will follow the trajectory etched in space-time. If you oppose this flow, like a kid holding onto his paper boat, the resistance you feel is the weight of that object. What determines the flow lines at each point? The matter and energy in the universe as dictated by Einstein's equations. Here's a simple example of a complete Newtonian problem. The mass is attached to a spring. It is pulled by a certain amount x and then released. What is it going to do? Newton says F equals ma, which in this case becomes m, acceleration, really. So that derivative is equivalent to k in the spring problem. Everyone clear? Proceed, we must know m and k, and I have already discussed how these are measured. Now we have a mathematically complete problem. Find the function x of t, whose second derivative is equal to negative k over m times the function x of t. Yeah, so they just, that equation we can't quite see, they just change that up a little bit. Is equal to negative k over m times the function x of t. Then we go to the math department and say, what's the solution to this equation? This is a problem in mathematics, and the answer that it's going to be oscillating back and forth will come from doing the math. Later, we will do some of that math ourselves. For now, I'm simply pointing out that once we have stated the laws in mathematical form, solving for the consequences is a mathematical problem. Here is I'm surprised he didn't go through it there, but here is another example. Newton discovers the force of gravity acting on everything. Here's the sun in figure 3.2, orbited by a planet. At this instant, the planet may be moving at some velocity v. The acceleration of the planet is due to the force of gravity. And we should probably carefully look at this one, just since it seems like we're constantly coming up against this. The
Reminds me of a
various
certain
gravities.
video.
Looks a little cool on me to me.
So the acceleration of the planet is due to the force of gravity between the planet and the sun, which Newton tells you is directed toward the sun, proportional to the product of the two masses, and which decreases with distance as 1 over r squared. This completely specifies the left-hand side of F equals ma. That's the law of universal gravitation. Then again, because the second derivative of the position is connected to the position, you go to the mathematicians and say, what orbit is the solution to that equation? And they will tell you it is an ellipse. So, of course, Newton did not have. Also, if someone else wants to jump in to clarify something, any of these things, I can pause for a minute. But of course, Newton did not have mathematicians he could go to. He was the math guy. Not only did he formulate laws of gravitation, he also invented calculus and figured out how to solve a
He
differential
was
equation
the
that came out
math
of his
guy,
F equals
sorry.
ma.
He was the math lad.
Yeah.
Never stolen a single equation.
Yeah. Just separate question. Does anyone know much about Leibniz? The other guy that was supposedly huh?
No, never heard of him.
Oh, well, surely somebody has. I mean, he's equal at the same time as Newton. Leibniz also was simultaneously coming up with much of the calculus.
The other
And I don't know that
calculus
much
lad.
about him either. What's that?
The other calculus lad. He like invented calculus at the same time as Newton, right?
Yeah. The German guy, and he had some other ideas, but yeah, supposedly he invented at the same time. So I've always wondered why Newton gets all the credit. And given how often we see that in history, like with Edison and Tesla or something, I've just sometimes wondered if Leibniz didn't get short shrift.
It must have been
He did the
Newton's
whole thing at
choice
the same
of
time.
high-heeled shoes. Or
Probably
rather,
so.
Einstein's. I take it that way.
Yeah. And I'm sure the Queen loved Newton's shoes. And that.
But yeah, I can't believe calling. He was the math guy. Like literally.
Yeah.
Every single equation he ever published was just stolen.
Yeah.
Oh, that's pretty funny.
It seems like all the people that are elevated that we know about are usually the people that are.
Oh wait, I'm sorry. I'm thinking of.
I
We're talking Newton. My bad. For some reason, I thought we were talking Einstein. My bad.
Yeah, I was gonna say, wait, do you have Newton gravy? Did
No, I don't have any magical Newton gravy. Newton, I think Newton's just not a. I think Newton's just a collection of works.
He's totally fictional as far as I'm concerned.
Yeah, pseudo
like.
historical. Yeah. But yeah, my bad.
So you don't think Newton is an actual figure? Then you think that Newton?
I mean, I'm
like a
open
bunch of
to
people
it. I'm
contributed.
open to it, but I think he just wrote way too much for one person and like way too much profound stuff.
He's the Johnny Appleseed of physics.
Yeah.
Well, as far as stealing stuff, though, like if he was Einsteinian in that way, investigating this Leibniz thing, he may have, or his group under him may have. It seems like Leibniz might have gotten ripped off. I'm not sure, but anyway.
Yeah, it's an interesting thought. I never looked into that much.
So continuing on the Newton accolades, we'll finish up. There has been no one like him. I speak of Newton the scientist. Newton the man had many flaws.
Oh, was he a
funny. A funny ending.
Yeah. All right. 3.4, Newton's third law. The third law says that if there are two bodies called 1 and 2, then F12, the force on 1 due to 2, is minus the force on 2 due to 1. Action and reaction are equal and opposite. Coulomb's law and the law of gravity both have this feature. You may assume it for every force in this course. We are now going to put the laws to work. You have to be good at writing down the forces acting on a body. That's what all these problems are going to boil down to. Do not forget the existing forces and do not make up your own forces. Yeah, don't want to do that. I've seen both happen. Every force, with the exception of gravity, is a force due to direct contact with the body. A rope is pulling it, a rod is pushing it, or you are pushing it, you are pulling it. One block is pushing another, and so on. Gravity is one force that acts on a body without the source of the force actually touching it. Later, electromagnetic forces can come in, but not in this book. That's it. Once more, with feeling. With the exception of gravity, all forces we will discuss in this book will be contact forces. We're going to begin with simple problems in mechanics. They will get progressively more difficult. Let's start with our first triumph. There's some object of mass 5 kilograms, and I apply 10 newtons on it. What's the acceleration? Everyone knows it is A equals 10 over 5 equals 2 meters per second squared. We have done this before, but I hope you understand how we know the force is 10 newtons and how we know the mass is 5 kilograms. The algebra is, of course, very trivial here. Next, I have a 3 kilogram block placed against the 2 kilogram block, and I'm pushing the former with 10 newtons, as shown in figure 3.3. I want to know what happens. One way is just to use your common sense and realize that these two blocks are going to move together. You know intuitively that if they move together, they will behave like an object of mass 5 kilograms, and the acceleration will again be 2 meters per second squared. What about gravity? What about the force due to the table on which the masses are moving? Imagine that this occurs in outer space where there is no gravity and no need for a table. There's another way to do this problem, which is to draw free body diagrams. Here, you can pick any one body that you like and apply F equals ma to it, provided you identify all the forces acting on that body. We'll first pick the 3 kilogram mass. My 10 newtons is certainly acting on it. What other force is acting? The force of the 2 kilograms, which has a magnitude F acting to the left. Do not include the force exerted by the 3 kilograms on the 2 kilograms. Next, consider the 2 kilogram mass. There is the same F, but acting to the right by the third law. Here is the mistake some people make. They add to that the 10 newtons. They feel that the 2 kilograms will surely feel it, since that is what is behind all the acceleration. It will be a mistake. That's an example of adding a force that you should not be adding. The only force acting on this little guy is this little F. So now we do F equals ma for these two guys. 10 minus F equals 3a, F equals 2a. N equals 5a upon adding the previous two equations, a equals 2. Notice I'm using the same acceleration for both. I know that if the second mass accelerated faster than the first one, then the picture is completely wrong. It will not feel the force due to the first. If it accelerated less than the first would have plowed into the second. If that also cannot happen, they're moving with the same acceleration. There's only one unknown, a. Once you got a equals 2, you can go back to equation 3.11 and obtain F equals 4 newtons. Now we know the full story. 4 newtons acting on 2 kilograms gives it an acceleration of 2 meters per second squared. 10 minus 4 equals 6 newtons acting on the 3 kilograms gives the same acceleration equals 2 meters per second squared. Just quick water.
This is where I don't know if he's going to go into the term, but you're going to hear expressions like rigid body, inelastic collision, and the like. And this is the things that apply right here.
Yeah, this definitely seems out of the rigid body focus. Because it's basically with the 10 newtons, I mean, even though it's two separate masses, that force, applies. Yeah. Sorry, not helpful. Here's another variation shown in figure 3.4. I have a 3 kilogram mass attached by a rope to a 2 kilogram mass, which I pull with a force of 10 newtons. Again, your common sense tells you that I'm pulling something whose effective mass is 5 kilograms. The answer is 2 meters per second squared. Let's confirm that systematically by using the free body diagrams in the lower half of the figure. Now there are really 3 bodies here. I want to get into the 3 body problem. The 2 blocks and the rope connecting them. In all these examples, I assume the rope is massless. We know there is no such thing as a massless rope, so what we mean is a rope whose mass is negligible compared to the 2 blocks being pulled. We'll take the idealized limit where the mass of the rope is 0. The 3 kilograms is being pulled by the rope to the right with a force that I'm going to call T, which stands for tension. The rope is being pulled backward by the 3 kilograms with a force T by the third law. What is the force on the other end of the rope? What should that be? If you said T, that is right. Not because the rope would snap otherwise. Something else will be a problem. If the 2 forces on its ends don't cancel, you have a net force. What are you going to divide by to get the acceleration? 0, right? So a massless body cannot have a net force on it because its acceleration would then be infinite. Massless bodies will always have equal and opposite forces on the 2 ends. In the case of the rope, This is called the tension on the rope. The tension is not zero just because this T and that T cancel. Suppose you're being pulled by my favorite animals, the elephants, both sides by equal and opposite forces. You won't find any consolation in the fact that these forces add up to zero as you get subdivided.
Did you all catch the Jedi mind trick he laid down there with the massless body? That's going to line you up psychologically with the massless particle to come.
Ooh. We're setting up some
Yeah.
nulls.
Ooh.
The old massless body.
The same types of mental manipulation are used to describe the analogies they put underneath to prop up things like time dilation.
What
All
even
that
defines
nonsense.
What even defines a massless body in a world without free space?
There
Not
literally
or
cannot
absolute
be
space.
anything called a massless body other than defining a zero density area or volume of space. You know what I mean? And that's not a body. That's a nothing. That's a not body. It's because it has no mass. It's a not thing. And this is how they snag the academicians. They
What?
get them to regurgitate this mantra.
Think about how much worse it is that it exists within a not space. It's like a double paradox.
Yeah, it seems like they should declare a massless body equals nothing, just zero. Like, doesn't
Exactly. It's
exist.
not a body if it has no mass. You know, that's the deal.
Yeah,
You're
yeah.
just
Like, why are you
defining a
bringing it up?
volume of space with nothing in it.
Should we continue?
Yeah, sure. Do you wanna? Let's see here. Oh, we're really close to the end of this section, so let's.
Yeah, I was going to go to the end of this one and then beg out if
Yeah,
I.
take it to the finish line. You're doing awesome, man.
Yeah, you're doing great.
Okay. All right. Cool. All right. So now you can invoke F equals ma for the three objects starting from the left. T equals 3a. T minus t equals 0a. 10 minus t equals 2a. We add the three equations and we get 10 equals 5a, or a equals 2 meters per second squared, and t equals 6 newtons. So the tension on the rope is 6 newtons. This is very important. When you buy a rope, the specifications will tell you how much tension the rope can take before it will snap. Your plan is to accelerate a 3 kilogram mass with an acceleration of 2 meters per second squared. You better have a rope that can take the tension of 6 newtons. If you see the rope in isolation, you find its acceleration is indeterminate according to equation 3.15. This is correct. It is the non-zero masses that determine A for everybody, and the rope goes along with this A for free. Now, non-zero masses are now applying to the ropes. I mean, they're
Yep.
macroizing it. Anyway, actually, I could probably go a little more if you want me to.
Yeah, it's if you're down, no pressure whatsoever. But if you want to keep going, yeah, by all means.
Yeah, I'll go one more.
Cool.
Cool.
Whoops,
All right. 3.5.
All right, go ahead.
You good?
Yeah.
3.5, weight and weightlessness. Now let's see what happens when you ride an elevator. In figure 3.5, you are the stick figure standing on the weighing scale on the floor of an elevator that has a positive upward acceleration. What will the scale register? We will draw free body diagrams as in the right half of the figure for you and the massless spring. The spring is being pushed down by you with a force W and up by the floor with the same force since it is massless. It will compress by an X such that W weight equals Kx, and X will somehow be displayed by a needle or digital readout. We should note a subtle thing that you may not have realized. Every massless spring is pushed or pulled by equal and opposite forces, plus or minus F at the two ends, since otherwise it would have acceleration equals F over 0 equals infinity, or this is like just totally undefined, I think, right? I mean, it's not even
Yeah,
necessarily
that's
infinity.
a broken equation. F over 0 doesn't equal infinity. It's a non-compute.
Yeah,
You can't divide by nothing.
Yeah, just period. Like, yeah, it doesn't equal infinity. It's nonsense. But so which of these two appears in F equals negative Kx? Recall the mass spring system. One end of the spring is anchored to the wall. When we pull the other end by X, we apply a force F equals plus Kx to the right. The wall exerts a force F equals negative kx at the other end. In response to the plus kx we apply, the spring exerts a force F equals negative kx on us, or on the mass attached to it. And that is the F we are using in writing down F equals ma for the mass. Good? Yeah. So the equation describing you in the elevator is weight minus mass times G equals ma, which means W equals m times G plus a, total acceleration. If the elevator is standing still and a equals 0, we see that W equals mg, which is just your weight. If the elevator is accelerating upward, W equals mass times gravity down plus the upward acceleration. And the needle will show a number greater than your weight. It will actually feel heavier. The spring not only has to support you from falling through the floor, but also has to accelerate you counter to what gravity wants to do. That's why we have the G plus A. You picked up some speed and are now coasting upward at a steady speed again, and W equals mg. As you come to the top of the building, the elevator has to decelerate so that it can lose its positive velocity and come to rest. So A will be negative now. If A is negative, then G plus A is less than G. Let us write in this case, A equals negative absolute value of A. Or actually, negative is really the opposite of, is how we should, be probably helpful to us to describe it as that, and not just always negative.
Well, in that case, though, it works just because it's an absolute value, right?
Exactly. Yeah. No. I was just thinking that in general. No, in this case, it's still going to be negative. Yeah. No matter what A is on the right-hand side there. So that W equals M times G minus the absolute value of A, which makes it explicit that the weight is less than the weight would have been. I mean, here we're getting to
less
Elon
than
Musk
zero state.
Yeah, we're getting into weightless stuff eventually. You will feel that your weight is reduced. On the way down, your initial acceleration is negative because you're picking up speed toward the ground. You'll feel less heavy. You can see that if the absolute value of A equals G, your downward acceleration is that due to free fall under gravity, and you will feel weightless. This can happen when the cable is snapped. You don't feel any weight because your normal weight is the opposition the floor offers to keep you from falling through it. But now the floor is also falling at the same rate. It's wrong to think that when you feel weightless, you have escaped the pull of gravity. We all know that in a falling elevator, you definitely do not escape the pull of gravity. It's going to catch up with you in a few seconds. This goes for the people floating around in space stations. They have not escaped the pull of gravity either. They have just stopped fighting it. They are all accelerating toward the Earth at a rate of v squared over r equals g asterisk, where g asterisk is the reduced acceleration due to gravity at the radius r of the orbit. If they had really escaped the pull of gravity, their spaceship would be off to the far reaches of the universe.
Boom. Thank you. Thank you very much, Scott. That was fantastic.
Yeah, no, cool. Absolutely.
Scott.
Well, excellent. Yeah, I hope everyone's getting a lot. How are we doing with it all?
I'll be honest with you, my brain's kind of fried. I'm gonna have to listen to it again.
You did great.
But you did great. That's what's important.
Thanks.
So yeah, what do you guys? In that case, then, you guys want to call it for the night?
Yeah, I'm good with that.
Yep.
Cool. Any final thoughts, questions that anyone want to throw out there for the live stream? Well, all right then.
Everybody's awesome.
If you didn't see earlier, go watch on Globebusters. Go watch Globebusters Tech from tonight. Check out on the orders of measurement. Alan gave a fantastic presentation. going through measurements of the quote-unquote speed of light, the induction rate of light, and going into all of the wonderful ways in which they tricked us into thinking that light could somehow magically be a particle at the same time as being demonstrably a wave. So go check that out. Alan did great. And also, tomorrow night, of course, is Friday night. So tune in for Flat Earth Fridays. You can join that live on X Twitter Spaces. Go follow Proud and Sacred. You can look up, if you need to look up the exact username, go look up Sacred at 100 @100 crypto keys with a K and a Z. And then go follow him, and then they'll usually post the link, and you can join there. Or you can just tune in to Space Audits or ADL, or possibly I will stream, I'm not sure. But tune in for one of our streams, and you can just watch if you'd rather just watch. And then that usually goes overnight into Stationary Saturdays. A lot of people come and go. And then on Sunday night, we may or may not do a Bring Your Own Brenner comp, or maybe some other kind of reading. We'll figure that out and put out the notice. So tune in for that on Sunday night. And then, of course, Tuesday, yet again, we'll probably keep doing on Mondays, we'll probably keep doing Twitter Spaces on Monday nights. So check that out as well, or X Spaces. And then, yeah, Tuesday, as always, Eat the Roundtables. I believe next Tuesday, Shane will be presenting on Sky Miles, and be on the lookout for other topics in the future, such as moonlight and climate change and seismology and, yeah, lots of other things. So, anyways, yeah, take care, everybody.